So let's go through a little bit of the theory of that, and we're going to cover sort of two of the main ways at which you go about doing optimal stopping problems. So the first thing we're going to cover is a specific stopping rule, which is optimal, called the one-step look-ahead rule. Okay, and then the second we're going to consider is in terms of stopping a random walk, which could be extended to different types of random walks. We've got this idea of kind of having a kind of concave function that decides the kind of boundary where you should stop. Okay, right. So let's go through the. Let's go through that. Okay. So after today, we'll sort of start to move away. So this is our kind of last week, or at least for now, for quite some time, we'll be working on kind of discrete time problems. So after this, we'll kind of move to continuous time control problems. And then quite quickly after that, we'll move on to diffusion control problems. Okay, so, most of the things you've been developing theory for are for doing stochastic calculus for integration. Okay, and so what we're going to do sort of after this is look at how those ideas combine with the ideas of control as well. Okay, and optimization. Okay, so we've sort of gone from dynamic programming, then we've kind of introduced randomness to it in terms of Markov chains to make Markov decision processes. Okay, we spent a bit of time developing the theory of Markov decision processes. Then we spent time for algorithms for solving Markov decision processes. Today we're going to concentrate on one specific type of optimal control problem, stopping problems. Then we're going to make time continuous, and then we're going to introduce diffusions into these kinds of controls. So that's sort of where we're heading. That'll probably take us until about the Easter break to go through all of that. Okay. Okay. So let's go through the optimal control stuff. Okay. So, and I'm not quite sure how big yeah, that's okay. All right. So optimal stopping. An optimal stopping problem is a specific type of Markov decision process. Okay, where there are only two actions. Okay, so it's a very simple one. There's an action, which means stop. Okay, so action, I'm going to call it A0 here. It could be the other way around. And A1, an action meaning continue. Okay, and here there are then two types of costs for this Markov decision process. So I'm phrasing it in terms of costs. It could also be done in terms of rewards. Okay, there's a stopping cost, which I'm giving by capital K or kappa x. Okay, and then there's a continuation cost. Okay, which is given by little c of x. Okay, so this defines something which we call a stopping problem. Okay. So notice we're not really controlling the process that we're observing, so we're not really necessarily influencing the environment, we're simply observing it and then saying now's a good time to stop. Okay? So if it was like something like a stock, it would be oscillating in a random way and you wouldn't actually be influencing its price necessarily. Okay? And then you might decide to sell some shares, for example. Okay? Okay. And if we assume that time is finite, then the Bellman equation for this type of problem, okay, where we're solving it over S time steps, so we did this previously actually in the examples class yesterday, is that we've got a Bellman equation of the following form. So if C is the cost function where I have to stop in S steps, so that guy, okay, so the optimal value function, given that I have to stop in S steps, okay, well, I've got two choices, okay, so it's a minimum cost problem, so we're minimizing, so that's why we've got that minimization here, okay. Then I've got two actions. I've got either I stop or I continue, okay. So if I stop, okay, the cost to me is capital K of x. Okay? And if I decide to continue, Then I've got an instantaneous cost of C of x, okay, plus the expected future cost. Okay. Note that there is no future cost if I stop because the game's over. So if I decide to stop, there's no costs there afterwards. You just have the cost at that time, the instantaneous cost of k of x, and then no cost thereafter. Okay? Whereas if you decide to continue, you've got a continuation cost, and then there's the cost from there afterwards with s minus 1 time units in order to stop. Okay? Does that equation make sense to everyone? So that's the Bellman equation for a stopping problem. Okay? So again, it's the minimum of the instantaneous cost for the action plus the cost from there afterwards. From here, there's no cost there afterwards because you've stopped. Okay? And here, we have a continuation cost plus the cost from there onwards. Okay? All right. And we work on an assumption that you kind of have to stop. So if you reach the final time unit, okay, so if you reach time C0, you have to stop. Okay, so if you've got no time left with 0 time units, then you just have to stop at that time. Okay? So it's not the case in these kind of stopping problems that you can wait and wait and wait until the end of time and then just not stop. It's like you have to stop at some point, and so the cost with 0 time units left is capital K. Okay? Okay, is everyone all right with those equations so far? All right. Okay, and what we're going to look into to start with is a specific rule, okay, called the one-step look-ahead rule. Okay, and in certain situations that is an optimal rule, okay, for a stopping problem. Okay. So, in the one-step look-ahead rule, here, okay, we basically do what the policy says. We look ahead one step, okay, and see, is it better to stop now, or is it better to go one step further and then stop? Okay? So let's say I'm at state X, okay? And let's say that I stop now. What's the cost? Capital KX. Yeah, thanks. Thanks, everyone. Yeah, okay. Okay. Now let's say I'm in state X, and I decide to continue one step further and then stop. Okay. What is the cost then? So Cx, yeah, so we've got a continuation cost, C of x. And then let's say I arrive next in state x hat, okay? And then I decide to stop there, so what do I do to this? It kind of says it below, but... okay, k of that, yeah? And I look at the expected value of that quantity, okay, from x, all right? So those are the two things that can happen. Either I stop, okay, or I go one step and stop. Okay? So basically what the one-step look-ahead rule does, it says, well, either I stop now and I get this cost, k of x, or I go one step further and then stop and then I get this cost. Okay? And if it's better to stop now, then I'm going to stop. Okay? So in other words, if this cost is lower than the cost of going one step further and then stopping, then I should stop. Okay? So it's a very kind of myopic rule. You don't look very far ahead. Myopic meaning like short-sighted like me. Yeah? You don't look that much further ahead than just in front of your nose. You look one step further and then make the decision. Okay? Okay? So that's exactly what this is saying. It's saying that I've got this set, S, okay? And that is all the states where the cost of me stopping at that state is better than the cost of taking one further step and then stopping. Okay? So that's what the interpretation of that set is. Okay? So in words, it says here, in words, you stop whenever it's better to stop now rather than continue one step further and then stop. Okay? So in a specific setting, that's actually an optimal rule. You don't need to kind of do this kind of backwards solving or have anything complicated that looks into the future too much further. That quite simple rule can be optimal in quite a lot of different circumstances. Okay? The specific set of circumstances which it is when this set S is closed. Okay? So I don't mean closed like in the topological sense of like a closed set or an open set. I mean closed in the sense of this definition here. Okay? So let's define what we mean by a closed stopping set. We say that a set of states, S, is closed if it's such that once you're inside that set, you cannot leave. Okay? So in other words, if I've got a state X, which is inside that set S, okay, inside, say, the stopping set, and there's no way that the process can reach a point where it's left the set anymore. Okay? So there's, for all S, X that are inside the set, and all Y that are outside the set, the probability of you jumping from X to Y is 0. Okay? Let's draw a picture of that. So basically, we've got some set. We've got some set S. Okay, and then we can imagine we've got our stock price, whatever, it wiggles around, but then once it's inside this set, it can't leave anymore. Okay? So once you've reached inside the set S, you're stuck. You've got to stay there forever. Okay? Okay. So what we're going to prove is the following result. Okay. That for a finite time stopping problem, so something you have to stop in, say, S steps, the set S, given by the one-step look-ahead rule, is closed. So if we've got a finite stopping problem and the set given by the one-step look-ahead rule is closed, then the one-step look-ahead rule is an optimal policy. Okay? In terms of your exam, it's just so easy to think of questions about this. So it's, you know, I always sort of give indicators. I think last year I asked a question in the coursework test and in the final exam on this. I'm not guaranteeing I'm going to ask you about it, but it's very easy to cook up examples where the one-step look-ahead rule is optimal. Okay? All right. So this, we're going to divide this into two parts. We're going to prove this property first in exercise 5.1, and then we'll go ahead to exercise 5.2 to prove that the one-step look-ahead rule is optimal. So this is just a little bit of a kind of interim result which we need to prove first. Okay. Okay. Okay, so first we're going to show that given the set S is closed, okay, that if the problem, the optimal cost function with S minus 1 steps and X is equal to K of X for all X, then it's also true for the problem with S steps instead. Okay? So it's sort of an induction argument. Okay? We're sort of saying, if the problem with S minus 1 steps is optimal to stop at X, then it must also be true for S. Okay? So let's show that. Okay? Okay, so let's go through that. So if X belongs to S, okay, then we also know that X hat belongs to the set. Okay, so if my current state is in this closed set S, then the next state must be in the closed set S. Okay? So let's write down the Bellman equation and look at what that means. So then, from the Bellman equation, we have that the optimal cost function over S steps, starting from X, where I'm going to assume here that X belongs to S. So I probably should say here that I'm assuming here that X belongs to S in this statement. And this should be for all X belong to S. Okay. Anyway, so the Bellman equation for this is I've got the minimum between the two actions. Either I stop, okay, and what is the cost of that? Kx, perfect. Okay. Or I continue, in which case the continuation cost is what? Perfect, yeah, thanks guys. Okay, plus the expected cost in the future. So what am I going to put in here? X hat, yeah? And X hat belongs to S, okay? Okay, and we've assumed that time S minus 1, with S minus 1 steps to go, that's equal to K. Okay? So this becomes okay. So if we're applying the one-step look-ahead rule, okay, and S is the set given by the one-step look-ahead rule, I should really specify that, where S, I should say S given by one-step look-ahead rule. One thing is I use the abbreviation OSLA for one-step look-ahead rule, okay, so O for one, S for step, L for look, A for ahead, okay? A slight correction there, okay? So if S is the set given by the one-step look-ahead rule, what can we say about the minimum of this guy? The minimum is given by Kx. It's better to stop now rather than go one step further. Okay? So that's by the one-step look-ahead rule. Okay? That's it. So basically it says if it's optimal to stop in S over S minus 1 steps, then it's optimal to stop in S steps. And then it's optimal to stop in S in the capital S in S plus 1 steps. So basically it's always optimal to stop in that set. Okay? Doesn't mean it's the only place you want to stop. At least we don't know that yet. Okay? So the next step is to show that this is kind of always the case. All right? All right. So now let's show the final part of the result. So if, for a finite time stopping problem, the set S, given by the one-step look-ahead rule, is closed, then the one-step look-ahead is an optimal policy. Okay? All right. So we know that it's at the last step you have to stop everywhere. Okay? Now suppose, so by exercise 5.1, okay, then Cs of x is equal to k of x for x belonging to S and S belonging to, let's say, the positive integers. Okay? Because I've said up here that if at the previous step the cost for everything in this set S is k of x, then it must be true for the previous one. And I know that's certainly true at the beginning because it's equal to the cost k of x for everything, which includes the set S. Okay? So I can just say, well, if it's true here, it must be true at C1 of x for all x belonging to S, and at C2, and so forth. Okay? So now, further, if x does not belong to S, so we know that it's always optimal to stop if we're in S. So it's always optimal to stop for x belonging to S. Okay. So let's suppose we got an element x that doesn't belong to S. Okay. So what does that mean? Well, that means that the cost of x, okay, is less than or equal to, is the cost of stopping is greater than the cost given by continuing one step and then stopping. Okay? So, if x doesn't belong to S, can you think of a better policy than stopping it then at x? So if x doesn't belong to S, why is it better for me not to stop at x? Can you think of a better stopping rule? So let's just interpret these two expressions. Yeah, that is the cost of me stopping at x. And x doesn't belong to the stopping set, so it satisfies this inequality. Okay, in fact, that should be a strict inequality. Okay. So what from this can you say is better to do? Yeah, from this, it's better to go one step further and then stop. Okay? So if you're not in the set S, you certainly should continue, because there's at least one policy that's better than stopping now. The policy that is to continue one step and then stop. Okay? So policy, continue one step, then stop, is better than stop. So stopping for X not belonging to S is never optimal. Put that up. Is never optimal. Okay? So, for all X belonging to S, it is optimal to stop. And for all X not belonging to S, it is optimal to continue. And that's it. That's an optimal policy now. We just say we've found, look at this one step look ahead set. If you're in it, you stop, and if you're not in it, you don't stop. Okay? Okay, so if you're asked a question with the one step look ahead rule, okay, you've got basically two things to do. You have to specify what the stopping set is, okay, and then you need to specify, show that that stopping set is closed. Okay, so once you enter a state, you enter the stopping set, you're never going to go back there again, okay? So there's two things to check. You need to check, you basically need to specify the set and then verify this closedness property, right? Then once you've done those two things, then you're done, okay? And you've got, I think, 2 or 3 questions on your exercise sheet to hand in to me next Friday, which ask you to essentially do that, okay? A bit of a hint for those question sheets. Remember that the state doesn't just need to be this X. You could define the state to be the X and the time, for example, okay? We'll probably see an example like that in a minute. But notice I could take a state of the system to be X and T as a kind of vector together. So that's a hint for one of the questions. Okay? All right. It's a bit of a hint. All right.